Welcome to this video on math with significant figures. We are going to add some numbers together. So when it comes to adding and maintaining the number of significant figures, the idea is that we don't want our measurements to come out looking more precise than they originally were once they are manipulated. So in my last video, I shared this. 1.2 looks like you had a graduated cylinder, let's say, that measured only to the whole number. And then you had to estimate what the next digit was. So how far the liquid level was between the measurement 1 and the measurement 2, and you estimated that it was about 2/10 of the way there. So that would be the estimated digit. The same thing is right here where this is the measured and then this is the estimated. And then what happened is that you did some math and now it looks like this hundredths place is actually the estimated digit and that your tool measures to the tenths place, but it doesn't. So that's why all of this significant figure stuff matters. And the idea is that the scientists have determined, I guess through trial and error, the best way to do math and maintain a level of precision when it comes to manipulating our measurements. Because most of the time we are manipulating measurements. It's very rare that you take a measurement and then just report the measurement. A lot of the time, especially in chemistry, you have to take the measurement and then throw it into an equation or into a data table, into a graph, whatever. And the data is going to come out manipulated. It's going to look like it is more precise than it originally was. So when it comes to adding and subtracting, the rule is the same. When it comes to the significant digits, we're focusing on the number of digits behind the decimal. So this one you're just going to add straight away because each of these numbers has the same number of digits behind the decimal. They each go to the tenths place. So you can add this totally classic, 0, carry the 1, and that's 4 and 4 is 8. So this comes out to exactly 8.0, and that is the measurement. It's not 8. It is not 8.00. It is exactly 8.0. Now here we have 2.5000 plus 1.8. We want to not gain any precision. It's okay to lose precision, but you can't gain it. So this might be annoying, but this is the way that it works. This first measurement, the 2.5000, has 4 numbers behind the decimal, where the 1.8 only has 1 number behind the decimal. We are going to focus on the measurement that has the least or the fewest number of digits behind the decimal because it is the least precise. So we are going to add these numbers together just as they are. I'm going to tell you to do this in the calculator because the calculator will give you all the digits. This comes out to 4.3. If you were doing this classic math, let's say, you'd have a bunch of zeros behind this. We don't want that to be the case. We want this to be 4.3, okay? And that's because this measurement has the least precision. We want our answer to match the level of precision of the least precise measurement. But let's say instead this was really 2.5123 plus 1.8. Still, we want our answer to match the measurement with the least amount of precision. Okay, the answer that you get here is 4.3123, okay? The idea is that we want to get the calculator answer and then round it to the appropriate number of significant figures. So we want our final answer to match the level of precision of that 1.8, meaning that we are going to need just one number behind the decimal. So we're going to keep this. We're going to take a look at that 1. The 1 is not large enough to round it. So even then, our answer would still be 4.3. So rounding to the correct number of significant figures is typically how that is done. You do all the math and then round appropriately. You don't just like chop off digits. In this case, they're zeros, so it's kind of easy to chop off digits, but there you have it. Okay, now for this example, we have 9.700 plus 10.4. When we are talking about adding and subtracting, we are concerned with significant digits, but we look at those in terms of digits behind the decimal. So the 10.4, even though it has more sig figs, only has one number behind the decimal. So we want our answer to match that and have one number behind the decimal. So we're going to add this together. The calculator is telling me 20.1, and I am inclined to agree with that. And this is going to be the correct answer because it has one digit behind the decimal, just like our least precise measurement. The same rules are going to apply for subtraction as well. So if we have this 4.5123 and subtract 2.8, again, we're going to put this in the calculator, and with subtraction, you'll probably see it a little bit better. Okay, the calculator is telling me 1.7123. Okay. I want my answer to have the fewest number of digits behind the decimal. It needs to match whichever measurement that is, and that is the 2.8 with just one number behind the decimal. So I need to get my answer to have one number behind the decimal. This 1 is not big enough to kick the 7 up to an 8, so my final answer would be 1.7. Again, the rules for addition and subtraction are totally the same. We are looking to have our answer match the measurement with the least precision, but that focus is going to be on the number of digits behind the decimal. When it comes to multiplying and dividing, you are going to focus on the number of significant figures. So you should put it in the calculator because the calculator is going to give you all of the digits, because sometimes we get a crazy number of digits. Right here, we would get 28.14. Each of these numbers has only, or rather, each of these measurements has only two significant figures. So we want our final answer to also only have two significant figures. In order to do that, that 28.14 will just become 28. When we divide, it is the same thing. You put it in the calculator. Calculator gives you an answer, and this answer is going to be a little bit crazy. 6.8 2916. I'm going to leave it here. 67. It's a bunch of sixes. This obviously is gaining precision as we're doing the math, which we don't want to happen. The measurement that has the least precision is this one right here, the 4.8. That has only two significant digits, so we want our final answer to have only two significant digits. This 2 is not large enough to kick that 8 up into a 9, so the final answer will be 6.8. Now here we have an entire equation, and we are going to work through this. This is going to be 300 with a decimal. So we're going to multiply 1.2 times 4.8. We get 5.76. 0.08206. When it comes to multi-step, we are not going to round until the very end. So this is 24.618 times n. And then we're going to divide each of these by 24.618. This answer here should have had two significant figures when we look at this, because the 1.2 times the 4.8 gave us this 5.76, but we don't want to round until the end. So we right here, even though we're doing the math with three significant figures, we want it to kind of reflect that we have two significant figures there. So it's really two sig figs divided by 5 sig figs, meaning that our final answer should reflect those two significant figures right there. Okay, and then when we solve for n, right, we're getting n by itself, leaving us with just n on this side. We are getting, for our preliminary answer, 0.2333975 5 going onwards. We want 2 sig figs here, so n is going to be equal to 0.23 because the second 3 is not large enough to kick that 3 up into a 4. So that is multiplying and dividing with significant figures. When it comes to the math, we are always looking to match the measurement with the least precision. When it comes to adding and subtracting, we're going to focus on the number of digits behind the decimal. When it comes to multiplying and dividing, we're focusing on just the straight up number of significant digits. When we're doing multi-step, we want to consider the significant figures, but not actually round until we get to the end because we want our answer to be as close to the correct answer as possible. And something to note is when we have physical constants like this right here, or we have quantities, we don't consider that when we're looking at counting significant figures. That 0.08206 is a physical constant called the ideal gas constant. That is a set number of significant figures. We're not going to consider it when we're looking at other stuff. And then if we're counting, so if we have a quantity of like 1, 2, 3, 4, 5, and you're literally counting them, that is considered to have an infinite number of significant figures behind it. So we won't even look at that when we're looking at the fewest number of significant figures. Because a lot of the time, if you were counting, you wouldn't actually write 3.00 to infinity. If I had, I don't know, a measurement of 2.5 and I counted that 3 times, there's really an infinite number of zeros behind here. So many zeros that my app doesn't want to draw. So because there's an infinite number of zeros back here, this is going to have the least precision anyway. So counted numbers, you ignore them when it comes to looking at the number of significant digits. All right. If there are any questions, leave them in the comment section below the video. Please subscribe so you don't miss the next practice session, and I'll see you there. Bye.